Gases in atmospheric chemistry. Air is composed of gases. Our atmosphere contains 78% nitrogen, 21% oxygen, 0.9% argon, and less than 1% carbon dioxide, roughly 280 parts per million, which is sufficient for sustaining plant life and allowing the growth of plants. The growth of plants proceeds, in fact, by the incorporation of carbon dioxide. That's the unit of carbon that plants incorporate to cause growth of anything that contains wood. That's how plants produce glucose. So it's amazing that such a low concentration of carbon dioxide produces growth. At any rate, we breathe, 21% of the air that we breathe contains life-giving oxygen, roughly 1/5 of the volume. Gases are completely mobile fluids that fill any container they are put into. Gases only occupy 0.1% of the actual space in the air we breathe. So, according to the kinetic molecular theory, the molecules that compose gases are in constant motion. They're bumping around at something like 400 meters per second. That's what creates the pressure of a gas. It's the transfer of momentum of the collisions of the air molecules. At sea level, that generates a pressure of about 14.7 pounds per square inch. So roughly, so for every square inch of surface area anywhere on the surface of the Earth, there's 14.7 pounds of pressure from the air. We don't feel it because we have the same pressure inside our bodies. Gas molecules mix together perfectly. For example, liquid gasoline and water don't mix, but their vapors mix perfectly and can actually make explosive mixtures which are dangerous. That's why we have to be careful when, for example, filling a boat with the gas tank of a boat, that the vapors don't go into the bottom of the boat and mix with the air, because then it creates an explosive mixture which is very dangerous. Gases are compressible. Like a spring or an elastic, you can compress a gas so that it'll store energy, which can be used to harness the compressibility. You can harness the compressibility of gases to make them do work, which is what we do in the internal combustion engine, and we use it in shock absorbers to absorb energy and then release it more slowly. So there are many applications where we use the compressibility of gases. Unlike liquids, which are not compressible, or very little. Pressure, when we're dealing with gases, we have to have a unit of pressure, and pressure is measured in pascals. It is a unit defined as a force of 1 Newton applied to an area of roughly 1 meter squared. A force of 1 Newton is roughly the weight of an apple in Earth gravity. So if you had a pressure of the weight of 1 apple spread over an area of 1 meter squared, that pressure is equal to 1 Pascal. 1 Pascal, in fact, is a very small unit. There's 101,000 pascals of pressure in 1 atmosphere. Now on the next board, the force exerted by gravity on a layer of air approximately 100 miles thick is enough to exert a force we call 1 atmosphere. 1 atmosphere, near the surface of the Earth. Interestingly, most of our atmosphere, about 90% of it, is below 10 miles altitude. We call that the troposphere. To give you an example of this phenomenon, airliners, jet airplanes like to fly at around 35,000 feet altitude so they can avoid the thicker parts of the atmosphere so that they can fly faster. If you want to memorize the concept of the atmosphere, think of 1 atmosphere equaling enough pressure to raise a column of mercury 760 millimeters high, which is a unit of torr. The torr is equal to 1 millimeter mercury. The pressure exerted by a column of mercury 1 millimeter high. So 760 millimeters mercury, 1 atmosphere is equal to 760 torr, equals 101,325 pascals, which is 101.325 kilopascals, which equals 14.7 pounds per square inch. If you're using a barometer, it equals 29.92 inches of mercury. So 29.92 and 760 are the same measure. And it's also, you'll see sometimes the bar, 1.01325 bar. 1 bar is roughly equal to 1 atmosphere. And the millibar is 1/1000th of a bar, so 1013 millibar is equal to 1 atmosphere. Regarding gas laws, because gases are compressible, and because they're compressible in a manner that is proportionate to the pressure exerted on them, One of the early chemists, by the name of Boyle, observed this law, and he put it in terms of a proportionality. Pressure times volume is equal to a constant. He found that if you had a certain amount of gas trapped in a bubble of a U-shaped tube, that if you put pressure on that gas, you double the pressure, you halved the volume. If you quadrupled the pressure, you quartered the volume, and so on. And the way he put that is pressure times volume of a gas is equal to a constant. Or if you like, so the volume of a gas is equal to a constant number times 1 over the pressure. Similarly, other scientists, Charles, came up with the idea that the volume of a fixed amount of gas maintained at constant pressure is directly proportional to its absolute temperature. They found that as you decrease the temperature a gas was exposed to, its volume decreased in accordance. And when that volume is extrapolated back to the lowest temperature you can achieve, you find that the volume of the gas falls to 0. So at absolute 0, gases turn into a liquid, so they stop occupying volume. Their molecular motion ceases. They no longer have any kinetic energy. And it also follows a constant. The volume of a gas divided by its absolute temperature is equal to a constant value. Finally, Avogadro's law, the volume of a gas maintained at constant temperature and pressure is directly proportional to the number of moles of the gas. So the volume of gas divided by the moles of the gas is also equal to a constant. Now you can combine all three of these laws, Boyle's law, Charles' law, and Avogadro's law, into what's called a combined gas law. The pressure, the volume, and the number of moles of a gas are all in direct proportion to a constant value. And the combined gas law states that the initial pressure, volume, and temperature and amount of a gas is equal to some other state where there's a different pressure, different volume, a different number of moles, and a different temperature, but it's all equal to a constant. Now this same law can be stated as PV equals nRT. If you simply transpose the NT to the R, you get PV equals nRT. So it's the same law, but stated in two different ways. This is for when you have an initial state and a final state, and this is for when you have a single state in which you want to find out one of the variables. Of course, you have to have all the other 4 variables to find out the 5th variable, and likewise here, there are 8 variables, so you have to have 7 of the variables to find out the 8th one. So we use this problem for solving problems with initial and final conditions. We use this formula for solving problems with one set of conditions. Another thing I'd like to point out is that the gas constant R varies according to what units you use, and we will explore that later in another lesson where we see what the values of R can be. Popularly, we find 8.314 and 0.08201 as the numbers that most often come up. But that'll be reserved for another lesson.